Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently doing a postdoc at the University of Helsinki in the Helsinki Institute of Physics, and I study cosmology. So that means that I study the universe, the content of the universe, how things evolve, how things interact, the history, the evolution, kind of the story of what is the universe, how did we get to where we are, the recipe and ingredients to build your own universe. That's what I study. Makes it sound a lot fancier than it is. So, yeah, I'm a theoretical physicist. I specialize in cosmology, and I love chatting about the universe and about cosmology and about science. I think sharing the amazing science that I do is one of the best things about being a scientist, because science is all about collaborating with people and chatting to people about cool topics. And I love chatting to everyone about all of the cool work I get to do. Hey Ange, hey Scott, great to see both of you. Thank you for joining as always. So welcome back to any regulars and welcome to any first-time viewers here. Anyone who's joining after seeing me on Friday, welcome. Glad you came along today as well. No worries, Scott. It's always nice to have you here for however long. Catch the replay. Replays will always be up on YouTube as well, so no worries. So yeah, hello if you're new. Welcome back if you're a regular viewer. If you haven't done so yet, please do subscribe to the YouTube channel, like this video, leave a comment down below. It really does help with engagement and it helps boost my viewers, which means I get to chat to even more people about science, which is very, very cool. Hey, Paul, great to see you as well. Always nice to see you. I know I can always count on you people being here in the audience. Thank you for your comment here, Mito. So I did a seminar, a webinar for the iTelescope network on Friday, and it was really, really fun. It was about, with the title of What Goes Bump in the Early Universe, and it was a review of the first 3 minutes of the universe. It was super fun. I got some really cool questions afterwards, and the replay is already on YouTube. I will share out the link later on Twitter, on Mastodon, and I'll leave it in a comment to this video. So whichever platform you're using to watch me, I'll share the link so that you can find me there as well. But it was great fun. I got some really cool questions, and it was just so nice to chat to people about some cool topics, as always, as you might be gathering by now. I love chatting to people about science and about cosmology. And I just want to acknowledge one comment here. I saw a comment from Ange about nice fluffy jumper. It is still nice. It is still fluffy. I still really like this this jumper. The graphics were really great. Thank you for that, Paul. I honestly spent a lot of time preparing the slides for the talk on Friday because it was the first time I was giving that talk. So I'm very glad you liked the graphics. I did put way too much effort into making those slides. So I'm glad they were well received. See another big comment here. Let me get to the big comments. Happy to tag along with the podcast. I'm a physics student from the Netherlands who has been subscribed for some time now. I'm planning on doing my Masters of Physics at Aachen. Well, that is a great choice. I did my Masters and my PhD in Aachen, in the RWTH Aachen University, the westernmost university in Germany. It's a really lovely place. They have some really cool cosmology courses. They have some really cool astral particle courses. So it's absolutely a great place to do your master's thesis and to get to know some amazing people. I did my Masters and my PhD in Aachen. The city is lovely. The university is really nice. And there are some really nice people there. So it's definitely a very nice place, very nice place to go. Walking to cafe will participate soon. I love the thought of some of you watching me from a cafe. That's just like really cool. Like you go to a cafe, you get coffee, you chill, you relax, and you watch your Sunday Science. Time for Sunday Science. So yeah, welcome everybody. Great to have you here. And there's a couple of things I want to talk about today, and I put it under the umbrella term of problems in cosmology. Hey, David Dunn, didn't see you in the comments. Great to see you here as well. So a bunch of people joined at the same time, and I miss you, but hello and welcome always to the regulars, and hello and welcome to first-time viewers. So today's topic is actually kind of motivated by the talk I gave on Friday for the iTelescope network, where I talked about what went bump in the early universe, and at some point I stopped and talked about all of the big open questions that we have in cosmology today. And there's really quite a lot of them. And this is fun because there's some questions that we might find the answer to, and there's some that we may never find the answer to. I think that's cool because the day we know all the answers is the day science stops being fun. The fact that there are so many things that we don't know and we might never know is what keeps us all guessing and keeps us doing what we do. And the day we figure out everything, will be very, very boring. So yeah, you need a stirring mug with your drink. Absolutely. You will need like space themed mugs when watching me. Some point, I know people have mentioned it in the past, at some point we should start like a Cup of Cosmology shop where you can all get your branded mugs, and then I become an actual brand. And yeah, someday maybe I'll set up a Cup of Cosmology shop, and then you can get all of the stuff with the cool logo and the banners. So I'm a cosmologist. I study the universe. So the first question we have to ask is okay, what do we know about the universe? What can I tell you about the universe? We actually know quite a few things about the universe. CMB much, we absolutely need CMB much. I had a conversation with someone at work the other day about getting a CMB jigsaw, like the actual CMB image, the cosmic microwave background radiation image, this amazing one here, in case anyone's forgotten what it looks like. Getting this made into a jigsaw, and then having like a 1,000 piece puzzle of this, it would be ridiculously difficult to solve, but I would absolutely love it. So at some point, if someone wants to get me the perfect gift, get me the CMB as a jigsaw. I will be incredibly happy with that. Branded mugs and fluffy hoodies, yes. Yes, and I could do the, seeing as I'm in Finland and Finnish people love woolly socks, maybe I should actually do branded woolly socks, because then I can be full on finished. CMB and Cup of Cosmology mugs. Yeah, I know it's on the wish list. It's on the long-term plan. Someday, maybe we'll come back to it. Who had 7 minutes? Yes, 7 minutes. Didn't take long for the CMB to appear. To be fair, the CMB was going to appear later on, but it came up in conversation. So, okay, let's do this. CMB, cosmic microwave background radiation, for anyone who doesn't know what this image is. This is the oldest light we can see in the universe in any direction we look in the night sky. This is the afterglow of the Big Bang itself. What we're looking at here is the temperature differences of photons, the temperature differences of particles of light that were produced in the very early universe and broke away from everything else 380,000 years ago. This actually does tie into what I was about to say, because what I was about to say is, what do we know about the universe? And we actually know quite a lot about the universe. And one of the main ways we know things about the universe is by using this amazing image, this snapshot of the baby universe. By looking at the statistical properties of this map, we can understand the properties of the early universe. So what we're seeing here is the temperature of these background photons, and there are tiny, 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 tiny temperature differences of 1 part in 100,000. So this is at an approximate temperature of 2.73 degree Kelvin, which is minus 270 Celsius and minus 440 Fahrenheit. And the tiny, tiny, tiny temperature differences you can see here are of the order of 1 part in 100,000. So it's very tiny temperature differences, but thanks to these temperature differences, we have galaxies. So the same mechanism that set the seeds for the CMB also set the seeds for galaxies that we observe today. So we can actually tell a very nice story from the early universe through the CMB to the formation of galaxies. And that's really, really, really cool. A puzzle that is isotropic and homogeneous sounds impossible to solve. Yeah, but it would be really fun, right, to just try and do a CMB puzzle. And then when you're done with it, you can frame it and put it on the wall. Okay, I see one question here about QFT and GR. I will come back to that soon. How do you know it's actually light from the Big Bang and not completely incidental radiation from present stars? I really like this question. This is an excellent question. Thank you for this question. And this CMB radiation, so what you're seeing here is basically a projection of everything around us. So you can actually put the Earth in a similar projection. This is kind of a hammer projection that we call it. And this is basically a sphere around us. And you can see that this is the same in any direction you look. If you were to have stars or galaxies here producing these photons here, you would have different splodges. You would have some regions where you have the photons and some where you don't. And you'd have more visible ones for galaxies that are closer, fainter ones for galaxies that are further away. But the biggest way we know this is that all of this light is in the microwave range of the electromagnetic spectrum. So light behaves both as a particle and as a wave. And as a wave, it has a wavelength. Now, we have the electromagnetic spectrum going from one range to the other. I'm just looking for the corresponding photo because I have it somewhere here. We have the electromagnetic spectrum with very high energy rays, known as gamma rays, short wavelength, going all the way down to radio waves, which are lower energy, larger wavelengths. And you see in the middle, we have the microwave one. I was about to point at it with my mouse, and I just remembered you can't actually see my cursor here. So this cosmic microwave background radiation is everywhere in the universe. It's isotropic, which makes it quite hard to point to a specific thing and say this is coming from this galaxy or from this star. And it's in the microwave range of the electromagnetic spectrum. As light travels throughout the universe, it gets redshifted. Its wavelengths get stretched. As it gets more and more stretched, it shifts to lower and lower energies. Much like you can imagine a wave. Slinky Toy had to come out. You can imagine a wave, as this is a photon, a particle of light, or anything that has a wave. As it's traveling throughout the universe, this is going to gradually expand and expand and expand, gradually shifting it into the microwave range of the electromagnetic spectrum. Any light that is produced by stars or galaxies hasn't had time to be redshifted to the microwave range. The fact that it's in the microwave range of the electromagnetic spectrum allows us to say that this light was actually produced 380,000 years after the Big Bang and has been traveling freely throughout the universe since that time. In fact, if we bring up the history of the universe, or as some people like calling it, I know there's another name for this, but history of the universe plot, you can see we have today on the right-hand side 13.82 billion years, and if we go to the distant past, we have the Big Bang. And then at some point in the middle, around 380,000 years, you can see this slice of the CMB, which is called recombination. This is the time when electrons could combine together with the primordial nuclei of hydrogen. So the protons and the electrons combine together to form hydrogen. And at this point, the photons can't interact anymore, so they gradually break away and start traveling throughout the universe. So how do we know it's actually light from the Big Bang and not completely incidental radiation from present stars? The fact that it's uniform everywhere in the night sky, the fact that it's in the microwave range of the electromagnetic spectrum allows us to put a date on it, and it is a prediction from our Big Bang model, and our Big Bang cosmology explains why the CMB looks the way it does. So that's kind of how we know that. So just want to, what's the other name? Yeah, someone in the chat can tell you because it is an inappropriate name, and I do try to keep my shows family friendly. Doesn't always work. There's always inevitably some cursing and some rude comments that slip out, but I do try to keep this show family friendly most of the time. Otherwise, I need to start putting disclaimers on YouTube. Well, actually, all of my YouTube videos have the big disclaimer, not meant for kids, just so there's no confusion. Going back to the question here that I overlooked because I wanted to answer that one. One of your favorite branches of physics is general relativity. Great choice. General relativity is amazing. I know that another big one is QFT. Do you need to utilize QFT in some way during your current or previous research? So I'm going to be honest. I never took QFT during my studies because it's a terrifying subject. It is extremely complex. It is extremely mathematical. And I knew who was teaching it in Aachen, and I did not want to take that course. You didn't have to in Aachen. There's two different branches, and I managed to always successfully avoid QFT. Quantum field theory, for those wondering what QFT is. So it's basically taking fields, so the quantum world, and making it into fields that are everywhere in space-time, and then you do some complex mathematics and you pull the standard model of particle physics out of there. Magic, absolute magic. Now, I always managed to avoid QFT, and focus on general relativity, on astronomy, on cosmology, on astrophysics instead. Curiously, now I'm actually not in the cosmology group in Helsinki. I'm actually in the computational field theory group, which is basically taking quantum field theory and throwing it at a computer, which is interesting. So I would say that I have since had to kind of learn some concepts of quantum field theory for myself. So I would say that it very much depends what type of research you want to do. But it's definitely good to know some parts of QFT. And especially if you want to work on bringing quantum world and GR together, some QFT knowledge will be useful. But as I said, I avoided it. And if you want to talk more about the courses in Aachen and stuff like that, feel free to message me privately and we can chat about that as well. So at some point I said, I'm a cosmologist. What do we know about the universe? And what we know is that the universe is about 13.82 billion years old. This is one of the things we know. We know the current composition of the universe. Wrong direction, sorry. Meant to go to that one. So we know that the universe currently has about 5% normal matter, about 26.2% dark matter, and about 68.9% dark energy. So these are the three main ingredients that make up the universe today. Normal matter is everything you see, everything from the stars in the night sky to me, to my tea mug, to the Slinky toy. All of this is normal matter. But normal matter only accounts for 5% of the energy budget of the observable universe. Dark matter, this next big 26%, is this type of matter that interacts via the gravitational force but doesn't interact via the electromagnetic force. This means that we can't see dark matter in any way because dark matter is basically invisible. It does not emit light, it does not reflect light, it does not absorb light. So it is very, very difficult to actually study dark matter, but we're pretty sure it's there based on the way it affects other things. And then the remaining 68.9% is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and we know pretty much nothing else about dark energy. But then we also know the history of the universe. We have a pretty good understanding of what's happened in the universe. Again, going back to the history of the universe map here, we know that the universe is 13.82 billion years old. We know that at some point galaxies formed. We know at some point the first stars formed. We have a pretty good understanding of the cosmic microwave background radiation and everything that's happened since then. With the exception of the big funky era that we call the Dark Ages. The Dark Ages are a fun era where we can't really get knowledge from, information from, because it's dark, as the name implies. But before I jump into the Dark Ages, of course, we can ask ourselves the question of how do we know all of these things? And going back to my favorite image, the way we know a lot of these things is through the cosmic microwave background radiation. So we know that the universe is 13.82 billion years old. We know that it has 5% normal matter, 25% dark matter, 69% dark energy. We know when the first stars began to turn on, and we know the initial conditions that set rise to the CMB. And all of this we know thanks to the cosmic microwave background radiation. So there is a lot that we do know about the universe. There is a lot of things that we have understood. And not just the cosmic microwave background radiation, right? If I bring this up again, you can see that later on we have galaxy evolution. So by looking at how galaxies evolve in the universe, we can understand galaxies as well. And then if we go to the very early universe, in the very early universe, we were dominated by the laws of particle physics and the four forces in the universe. So by studying how particles interact today and how they behave in extreme energies and extreme temperatures, we can get a good understanding of what happened in the early universe. So there is a lot we do know about the universe. And usually on this show, that's what I talk about, is the stuff that we do know. But there's also a lot we do not know, and that's the problems or open questions in cosmology. Let's see, there was another few comments. As always, if I miss your comment, I'm in no way intentionally ignoring you. You are welcome to ask your comment a second time. Sometimes comments get lost. I do try to scroll back and get to all of them, but occasionally I do actually miss comments, and I'm sorry if that's the case. It's definitely not intentional. Feel free to ask them again. Okay, you'll definitely reach out. Awesome, yes, please do so. On one of your previous comments, Aachen is indeed a beautiful city. It is. And there's a lot of nice things about Aachen, but there's one thing that I really miss, which is a chain of bakeries called Moss. They have something that I've only ever found in Aachen. I've been to a lot of other places in Germany. And it's like a sweet bread that has a crumble topping on it. And it is an amazing thing. And I haven't had one in years, and I miss them. And I'm considering doing a stop at Aachen at some point on a train journey just to nip out and get one of these snacks from Aachen. So yes, Aachen is a lovely place. Once you're there, check out Moss Bakery and look for this snack. If anyone's in Aachen, that's just general life advice. I know my way around cities based on where the best snacks can be found. Is there anything other than time that can mean? Oh, this is a long question. Let's see. Oh wait, there was another one there beforehand. I missed another one. On a random note, what are some of your favorite sci-fi concepts? Oh. See, the thing about sci-fi is it's a great way to disconnect. I love sci-fi shows. I'm a huge Doctor Who fan. And I like things like force field, laser swords, lightsabers. All of this is really, really cool, as long as we keep it in the realm of sci-fi. Once we try to explain physically how these things work, everything gets a bit weird. I think something that I would just love to have, just for the pure fun of it, is a holodeck. You could just see so much. You could do so many things. You could learn so much with a holodeck. You could bring up incredible scenarios and just play about and see what happens. So I think something that I would love to have is a holodeck. I don't think realistically we're ever going to get one, but that's something. And if anyone says it's like AI, no, it's not. Or virtual reality, no. I want an actual holodeck, not virtual reality. But anyway, someday maybe we will get there. Also, Aachen also has some scary, hideous statues. Yes. You'd like a sonic screwdriver? A sonic screwdriver would be really cool. You can do so many things with it unless you're trying to use it on wood, which is always a kind of a big disappointment that you can't sonic wood. Yes, a sonic screwdriver would be very, very cool. I actually have one. It makes noise and it flashes. It doesn't actually do anything. In fact, I am going to do something I never do, and I'm going to run away from the screen for 1 second just to get my sonic screwdriver, as we're on the topic of sonic screwdriver. And it makes noise, and it flashes, and it does literally nothing else, but I love my sonic screwdriver. So yes, I want a real one of those as well. Complete tangent there. I just went on a complete tangent to run off and get my sonic screwdriver. As people know, as my regulars know, it is very easy to throw me off track on sci-fi, sonic screwdrivers, Doctor Who references is a good way to get me completely off track. I heard the cinnamon buns are famous in Helsinki. I can absolutely confirm that the korvapusti, the cinnamon buns here in Helsinki, are amazing. And I can never get enough of them. And I had one yesterday as well. And I try to make like I can't go a week without having cinnamon buns. Yes, yes. The cinnamon buns in Helsinki are indeed very tasty, as are the cardamom buns actually. So yeah, I recently saw a korvapusti, a Finnish cinnamon bun that had been dunked in chocolate, like a chocolate covered cinnamon bun, and I resisted the urge to buy one because it just looked too unhealthy. But I'm going to go back and get one at some point. Okay, back to the topic. Sci-fi cinnamon buns, always fun. You want a sonic screwdriver? Yeah, I'm very happy with this one. Also, it comes with changeable parts. Like you might notice this is an amalgamation of Matt Smith's and older models, but this is complete modular, so you can change all the different parts. And you can actually build like 81 different combinations with the pieces I have. Yes. I am not being paid by the manufacturer. I honestly can't even remember where I got this from. It was a birthday present at some point. It's got no branding on it whatsoever. So it's in no way a paid advertisement. It's just a sonic screwdriver, and I love sonic screwdrivers. So it's not in any way a paid advertisement. The same as my Course Kazakh stuff is not a paid advertisement. I just have fun things. Can't even remember where I got my Slinky toy either, but Slinky toy is here as well now. I have all the props today. Your wife is making cinnamon buns. I am very envious. I want a cinnamon bun. Okay, back to physics. Let's rewind here because there were 3 physics questions together as well, and I missed those. Question from James. Is there anything other than time that can manipulate one wave into another wave type? Could we be fooled because of this? So I'm not sure what you mean by this of manipulating wave types from one into another. So, you can't turn a sound wave into a pressure. You can't turn a pressure wave into an electromagnetic wave. You can't turn an electromagnetic wave into a gravitational wave. So I'm not sure what you mean by a wave type here. There are some properties like the direction that a wave propagates in that you can change. You can change the polarization or the direction in which electromagnetic waves vibrate. But I'm not sure what you mean about changing one wave into another type of wave. So if you want to specify a bit what you mean there, maybe we can come back to that. Is there any theory that explains why an incredibly dense pre-Big Bang universe would expand? Thank you for that question, Ben. That is an excellent question, and that actually allows me to get back on topic. So I'm just going to make a very quick note of that because I want to answer the next question and then come back to this. A comment from Paul here. I'm always confused between space expanding versus matter accelerating. For an example, at the end of inflation, if it was space expanding, why did matter have lots of momentum as if it was an explosion? Okay, so actually these 2 questions are related to inflation, so we can get into inflation in a sec. Let me just catch up with the comments. Cinnamon buns, korvapusti, yes. Sonic screwdrivers. When the sonic screwdriver turned on, your shells fell apart. Sorry for that. Okay. Another inflation question here, though cosmic inflation is widely accepted at the moment, do you think these models might be tweaked in the near future or even disputed? Love the inflation questions. Yeah, it was a birthday present at my Doctor Who themed birthday party. Yes, I should specify that this was not only a birthday present, it was a birthday present at a surprise birthday party that my mother organized with my friends, because of course my mother was in contact with my friends, why not? And organised this Doctor Who themed birthday party that included me getting this, everyone wearing Doctor Who masks. Everything was Doctor Who decorated. We broke character and had lightsaber fights as well because we had lightsabers at hand. So it was a very cool birthday party, and that's when I got this. And I'm trying to think when it was, and I would say 2014. Yeah, I would no 2011, 2011 or 2010 even. It was either 2010 or 2011, so that's how long ago I got this. Okay, you're thinking of changing a photon into a microwave somehow. Okay, so in this case, what you're thinking about is just stretching the waves. So you change them, for an example, from gamma rays, which are high energy, to radio waves, which are lower energy. And this is something that you can accomplish either with photons traveling throughout the universe, where they gradually get stretched, or by photons climbing in or out of gravitational potential. If you imagine a photon is going to fall down a hill, then it's going to squash up, and when it climbs out of a hill, it's going to get stretched. So if you have something like a big clump of dark matter that creates a gravitational well, so a well in the fabric of space-time, it curves space-time, the photon will be redshifted as it falls in, and redshifted differently as it pulls out. Now, usually it falls in, gains energy, climbs out, loses the same amount of energy. But if in this process the well grows because the universe is expanding, it's going to change the redshift of the photon. So there are several things that can change the redshift of a photon, but it's mainly, or the wavelength, sorry, but it's mainly motion. So something either moving away from us, towards us, or traveling within space-time where everything gets stretched. Hope that answers your question. If not, we can come back to it. But there were several questions about inflation, and that does allow me to get back on topic. There was the TARDIS blanket was a different birthday. The TARDIS blanket, I have a 2-meter long fluffy TARDIS blanket. That was a different birthday. That was not the same birthday as the theme thing. And I think it was also a different birthday where I got the levitating TARDIS that I have. I have way too much Doctor Who much. Just realised that I'm actually wearing a Doctor Who t-shirt today as well underneath the fluffy thing. Okay, back to the universe. The only one we have access to. So, if we look at this picture of cosmic evolution, we know what happened today. We have a pretty good understanding of recombination until today, with the exception of the Dark Ages, and I made this comment before, so I need to go on to the Dark Ages. The Dark Ages is this fun period in between the CMB being produced and emitting light, and the first stars being turned on. In these Dark Ages, so after CMB, before galaxies formed, not much is happening. Because, well, a lot is happening in the universe, but there's no light. Because all the light from the CMB, from the cosmic microwave background radiation, so all the light from the early universe is broken away. And you don't get light again now until, back to the Hooniverse. We don't get light again now until the first stars form. First stars turn on and start emitting light. So there's this whole period between the CMB breaking away and the first stars turning on, which is a couple of million years, a couple of billion years even, we're not completely sure. And in this whole time period, it's very, very hard for us to figure out what was going on because we don't have light at that point. But what we might have is other processes going on that we might hope to measure someday. So I said we were going to talk about problems today. Problem number 1, what was happening during the Dark Ages? That is a question that we don't know the answer to. Okay, now going back, I'm going back in time here. We have recombination, but let's go right back to the beginning. We have the Big Bang and inflation. So what is the Big Bang? The Big Bang is basically the model that we use to explain the history of the universe. Big Bang is not a TV show, and Big Bang was absolutely not an explosion and not big in any way. It was an expansion that happened everywhere in the cosmos. So at some point, based on everything we see in the universe today, we think that at some point everything had to be closer together in what we call causal contact, so touching each other, a lot hotter, a lot denser. Now, this is what we call the initial Big Bang. However, in order for the universe to look the way it does today, so in order to explain why the universe appears to be flat and why the CMB appears to be at the same temperature, we need something else. And this something else that we add is inflation. So inflation is this hypothetical period of exponential expansion in the very early universe, where the universe went from being hot, dense, and smaller than it is today to being a lot bigger, a bit colder, and a lot less dense. Now, when I say that the universe used to be smaller, I want to add the caveat that smaller but still infinite, because the universe is infinite today. It was also infinitely big in the past, and we can talk about a smaller infinity than today, but the universe was still infinitely big even before inflation. It was just a lot smaller than it is now, but still infinitely big. So inflation is this hypothetical period of exponential expansion that we've added into our standard model of cosmology to explain why the universe looks the way it does. So during inflation, the universe grows exponentially. We've become accustomed to exponential growth over the last few years, unfortunately. So during inflation, the universe grows exponentially. But the cool thing about inflation is that it deletes the memory of anything that came beforehand. By its nature, inflation pushes everything far and far away. It changes the makeup of the universe completely. So if there was anything before inflation, it's not something we can actually talk about in any reasonable way. And here's another thing. We have no idea how long inflation lasted. We have a lower limit. We know we need a certain amount of inflation in order to explain the problems that we want to solve, like the flatness problem, the horizon problem, so why the universe is flat and why the CMB is always the same temperature. But we don't have any upper limit. So inflation could have lasted millions of years. It could have lasted billions of years. We do not know. And this is really cool because people, even in this image here, you see we put inflation ended 10 to the minus 32 seconds after the Big Bang. This is ambiguous because we do not know how long inflation lasted. That's another big question that we have, is how long inflation lasted. Do we know that the universe is infinite? We have no reason to believe otherwise. And the problem is that if the universe is not infinite, it means it has a boundary. It ends somewhere. And that would mean it separates universe from non-universe, right? If you have an edge to the universe, it's an edge that separates two things. But by definition, the universe is everything in existence. There can be nothing outside of the universe. So if you have a boundary around the universe, if it's a finite size, you have an edge, you have a boundary. And then that separates universe from not universe, but not universe doesn't make sense because that would also be part of the universe by definition. So by that idea, the universe must be infinite, and it must have been infinite before inflation, if there was something before inflation. So the cool thing here is we have this period of exponential expansion. We think we haven't been able to prove inflation yet. We haven't found the biggest piece of evidence for inflation yet. But we think there was this period of exponential expansion, but we do not know how long this lasted. It could have lasted billions of years. It could have lasted a fraction of a second. This is very interesting, I think, because then when we look at this map or this sketch and people say, okay, we start our cosmic clocks at the Big Bang and then we have inflation, it's actually not technically correct. We always start our equations, we start counting basically at the end of inflation. But we have some idea of what was happening during inflation. The universe was growing exponentially. But the meaningful time that we start counting is basically end of inflation, not start of inflation. So you could argue that Big Bang comes after inflation because this period of hot, dense thing is not really before inflation. It's something that is happening during/after inflation. So inflation, exponential growth in the early universe. I want to go back to the two questions on inflation we had earlier at some point. Getting distracted again by sonic screwdriver and cinnamon buns. So is there any theory that explains why an incredibly pre-Big Bang universe would expand? The theory, the model that we have to do this is inflation. We don't know exactly what triggered inflation, how long inflation lasted, or what exactly inflation looked like or how it behaved. We just know that it was some type of energy that caused the universe to grow exponentially. We think we haven't found the direct proof for inflation just yet, but if we didn't have inflation, we can't completely explain why the CMB looks the way it does and why the universe is flat. Then we also had the question from Paul about confusion between space expanding and matter accelerating. At the end of inflation, if space was expanding, why did matter have lots of momentum? And this is also a good question here. And so we reached the end of inflation. Inflation stops. We're not completely sure why inflation stopped, why we don't have eternal inflation, what caused inflation to stop. One idea is basically that inflation just ran out of steam. So you could imagine a ball on top of a hill that is going to roll down and reach a minimum. Now, if we're talking here about a potential energy, so let's say we have the ball at the top of the hill, you push it over, it doesn't take much, just some random bump, someone coughs, someone sneezes, the ball starts rolling down the hill. But then it's going to reach a bottom and there it's going to stop. If inflation happened in a similar mechanism, basically the field or the thing that caused inflation fell to a lower energy. Once it reached its minimum, it stopped and this ended inflation. But we're not completely sure. So at this point, the universe is expanding exponentially. The expansion of the universe is dramatic. It's happening everywhere in the universe. You have this massive exponential expansion. And things inside the universe don't necessarily have momentum at that point. They're not necessarily moving by themselves, but they will feel the ripples of what is happening in the cosmos. After inflation, at some point we produce particles and antiparticles. We're not completely sure how we produce particles and antiparticles. We just produce them. We think it might be related to the leftover energy of inflation converting into these particles, in which case you then produce them with a specific amount of energy, which then gives them this specific amount of motion, if that answers your question, Paul. So now we get to another few big questions that we have. We don't know what caused inflation. We don't know how long inflation lasted. We don't know what inflation looked like. We're pretty sure that inflation happened, but we haven't yet found the clearer signal for it. And the clearer signal would be ripples in the background of the universe in the form of primordial gravitational waves. So gravitational waves are ripples in the fabric of space-time. They are fluctuations of gravity. If a gravitational wave passes through you, you get thinner and fatter. Sorry, you get thinner and taller, and then shorter and fatter. You first go in one direction, then in another. But this effect is tiny. If a gravitational wave hits you, you will grow by a fraction of like a billionth the width of a human hair. It's a ridiculously small thing. So gravitational waves are a really cool prediction of general relativity. We have been able to measure gravitational waves of black holes smashing together, of neutron stars smashing together, but there could also be these primordial gravitational waves behind everything else in the background of the universe, which could be produced during inflation. Most inflationary models that we have should actually produce gravitational waves. And these would be so dramatic that they would actually affect the direction that the CMB photons propagate. So not the temperature of the CMB photons, but the direction in which they're vibrating, because they would have picked up some effect from these ripples in the early universe. So by looking at which direction the CMB photons are traveling in, they're traveling towards us, but they're vibrating in one direction, and this is what we call polarization. So by looking at the polarization in the CMB photons, we can try to look for the afterglow of inflation itself. We have not found it yet. We expected to by now. We have not, which does allow us to say a lot about inflation, because depending on how inflation happened, you should have seen these gravitational waves already. Okay, so I see the question here about non-baryonic matter and structure formation. Going to get to that. First big questions: inflation. What was it? What did it do? Why did it do it? How did it do it? Why did it end? How long did it last? So many questions about inflation. I'm just going to put that under the big question of inflation, question mark. And now we get to the creation of particles. We're producing particles and antiparticles. How did we produce matter? We did. We're not quite sure. We're figuring it out. But then we have the more important question of why did the early universe produce a tiny bit more matter than antimatter? So antimatter is like matter's evil twin. It has the same properties except opposite quantum properties. So if you have an electron, which is negatively charged, its anti-electron, known as a positron, will be positively charged. If you put an electron and a positron together, they're going to annihilate and produce photons, particles of light. And in the very early universe, we produced particles and antiparticles, but with a slight imbalance. For every 1 billion antiparticles, we produce 1,000,000,001 particles. This is very cool and very weird. we're very glad that this happened, because if this didn't happen, all of matter and antimatter would have annihilated. We wouldn't be here to have this conversation. But we're not exactly sure why there was more antimatter than antimatter, more matter than antimatter. In most of the scenarios we can come up with to explain the existence of these particles and antiparticles, you should create equal amounts, and yet we don't. So that's a big mystery. How did this happen? Why do we have more matter than antimatter? We don't know. Okay, so going back to my cosmic history map here, we've covered Big Bang, wherever that is. We've covered cosmic inflation. We've done the part of particles forming. But in addition to particles forming, there's something else happening in the early universe. I will get to the question about non-baryonic matter in a minute. So there's other things happening in the universe. Sorry, we produce these particles. Now these particles are going to start talking to each other, and they do this through the forces. So we know that today the universe is governed by 4 forces. We have the gravitational force, which we're pretty familiar with. I drop pen falls down. Earth stays in orbit around sun. Gravity, good. We like gravity. Then we have the electromagnetic force, electricity, magnetism. You know, I have light, I stick magnets to my fridge. I actually have little planet solar system magnets on my fridge. I love them. Electricity, magnetism, electromagnetism, we know how this works. Then we have the strong nuclear force. It's very strong. It holds everything together at the atomic level. It glues quarks together inside protons, and it glues protons and neutrons together inside atoms. Then we have the weak force, which is responsible for radioactive decay, and let's move on from the weak force. 4 forces, these are the 4 we have today. Out of those 4, there's one we don't understand, and that one is gravity. You'd think it's the weak force or the strong force, but no, it's gravity. We don't understand gravity. We don't know what gravity is. We don't know why gravity behaves differently to the other forces, but gravity. Glad that we have it. So gravitational, electromagnetic, strong nuclear force, weak nuclear force, 4 forces. This is what we have today. We know that at very high energies, like the energies we had in the early universe, the weak force and the electromagnetic force were actually combined together into one force known as the electroweak force. They were entwined, they were together. At some point, they separated. But we did have electroweak force, which means at some point there were only 3 forces. You had gravity, you had strong, you had electroweak. And then here's the question of, if we go to even higher energies, did the other forces unite at some point? We have very good reasons to believe that the strong force was also united with the other 2, so that at this point we would have had gravity and then strong electroweak, or electro-strong weak, however you want to call it. This theory, this model to unite these 3 forces, is what is known as a grand unified theory. We haven't quite figured that out yet. There's a lot of people working on it. And then if we go to even higher energies, was gravity joined together with the others in what is known as a theory of everything? And if so, how did this work? And we haven't been able to answer this question yet, because we don't know how to put gravity together with the quantum world. We can't match our predictions of the large universe with gravity to the intrinsically random behavior that we have in quantum mechanics. Gravity is deterministic, but quantum world is not. And how do you put these 2 together without running into issues? So next big question, how many forces were there in the early universe? How do we fit gravity together with the other forces? How do we get a grand unified theory? How do we get a theory of everything? We don't have the answers to these questions either. But again, we're glad that we do have these things. Going back to our map, okay, we've got particles forming, particles are now talking to each other. And now I want to talk about something that happened about 3 minutes after the Big Bang, or after the end of inflation, actually. And this is a time where you form the very first nuclei, atomic nuclei in the early universe. This is where all of the hydrogen that we have today and all of the helium that we have today started to form. And what happens here is the universe gradually cools down, and your protons and your neutrons can start fusing together, like the process that happens inside stars, where you fuse heavier and heavier and heavier elements. You could actually have this process in the early universe, where you fuse protons together to get different types of helium, like helium-3, which is unstable, or helium-4, which is stable. You can also produce deuterium, which is like hydrogen, but with 2 protons. So it's like a heavy version of hydrogen. And you can also produce lithium, which is one of the lightest elements we have in the periodic table of elements. So 3 minutes after the end of inflation, you produce the first nuclei. So you don't yet produce atoms because electrons aren't going to bind together, but you can produce the core. Sorry, they're not going to bind together into the atoms, but you can produce the nuclei, the core of these atoms. So 3 minutes after the end of inflation, you produce the main building blocks that are helium, hydrogen, and a lot of lithium in the universe. This is a really cool process because this is something we can actually observe. If we find galaxies that are really, really, really young, where stars haven't been able to produce much, in those places, you can actually get, yes, deuterium is a proton and a neutron, sorry, no, is it? Yes, deuterium is proton and neutron, not two protons. Two protons is helium. Proton and neutron is when you have deuterium, heavy hydrogen, basically. So 3 minutes after the end of inflation, we produce these primordial elements. And by looking at really, really young galaxies today, we can still get a snapshot of these early elements. And this is really cool because then we can, if you find a young galaxy or a galaxy where you haven't had many stars forming, you're not going to disrupt this balance of early elements too much, right? So then, yeah, light helium is 2 protons and a neutron. Yes, helium-3. Yes. So if you find, for example, a dwarf galaxy, a galaxy that doesn't have many stars in it, you can basically count how many stars it has, do some calculations based on how many stars I see and how I know stars behave. This is what should have been added to the galaxy since it formed. And then you subtract that. So you subtract the amount that you've calculated has been added by stars, and what you're left with is the primordial amounts. And you can do this to figure out how much of these primordial elements you had. So if we measure the helium in these galaxies, it perfectly matches our prediction from Big Bang cosmology. So if I draw this picture of the history of the universe and I calculate based on everything we know, this is how much helium should have been produced in the early universe, and then I compare to what I see in early galaxies, this matches perfectly. The same is true for deuterium. The amount of deuterium we predict and the amount we observe in galaxies matches. And then we can do the same for lithium. And here comes the problem. When we measure the amount of lithium in the galaxies, we find 3 times less than what we expect. 2 to 3 times less, which is not substantial, but it is also a factor 2 or 3. We have no idea why. This is a very cool thing. This is known as the lithium problem in cosmology. And we have no idea about this. There are some ideas that maybe we've just miscounted the lithium. Maybe we've misunderstood how lithium forms in stars. But we don't know the actual answer to this. And it's quite fun because this is a prediction from our Big Bang cosmology. We predict the amount of helium, the amount of deuterium, and the amount of lithium. And then you put it together and say, well, 2 out of 3 match, so it's good enough. But the third one is off. And that is something that, we probably want to come back to at some point. I realize I missed the question here, so let me just go back to this question. And I still have in mind that I haven't answered the non-baryonic matter question. That is still in my mind. How does time remain constant as expansion accelerates? So is time slowing down as well? I'm not sure what you mean here exactly, but yeah, when we talk about the expansion of the universe, we talk about expansion of space-time itself. So space and time are both expanding, but it's quite hard to quantify the expansion of time because time is always measured at the same rate. But like we move always at 1 second per second. So I'm not completely sure how we would quantify that, but yes, if we look at an object that is moving with the expansion of the universe, we need to always bear in mind that time is relative. Okay, when you say the amount of helium or lithium in a galaxy, does that mean a percentage compared to the other stuff in the galaxy, or are we predicting an actual amount? We are predicting an amount always relative to hydrogen. So you take hydrogen as your base, and then you say for every X amount of hydrogen, you should have Y amount of these other particles. And the amount of hydrogen is pretty well established, and then you use the other ones to kind of calibrate it. So it's always based on one thing, because of course this is going to depend on the size of the galaxies. So it's always related to, with respect to one base element, and then it's how much compared to other elements. So we always use hydrogen as our calibrator. But I just want to pause here, because this discussion of primordial elements fusing together in the early universe The other advanced societies, electric vehicle manufacturing, using up all the lithium. Yeah. We should stop using up eyes as well, especially given the conditions in which people are treated when they extract lithium. Not going to go in all rants. Make sure your lithium is fair trade and sourced in an eco-friendly and human-friendly way, because most lithium is not. Okay, lithium in planets, in universes, in galaxies, that's much more my area. But I want to pause on this discussion of these primordial elements, and I want to talk about Carl Sagan's famous phrase of "you are stardust." And this is very true. A human is made up of 65% oxygen, about 20% carbon, a bit of nitrogen, a bunch of other things, and all of this is formed in exploding stars. 90% of your atoms were formed when a star reached the end of its lifetime and exploded and propagated throughout the universe. So your atoms were formed in a star, and then when the star died, it spread them throughout the universe. But 10% of every human is in the form of hydrogen. Let me actually bring up the image for this. Here you can see on the left your periodic table of elements, on the right a sketch of what makes up your average human. And you can see here in the periodic table where everything comes from. Everything in orange and yellow and dark green and light blue, this comes from exploding stars. But if you look at the hydrogen at the top left, this comes from Big Bang nucleosynthesis. So this means that 10% of your atoms come from Big Bang nucleosynthesis, from the early universe. 10% of you that is hydrogen was formed 13.82 billion years ago, a few minutes after the end of inflation. Those atoms have existed in the universe since then. Today you're using them. When you're done with them, they will go back to the universe and go on to the next thing. I love this fact. We are stardust, but we are also universe dust. Nothing makes me feel closer to the universe than knowing that I carry atoms that were formed a fraction, like a few minutes after the Big Bang itself. This is absolutely amazing, and I love this. You are stardust, but you are also universe dust. You actually carry atoms from 3 minutes after the Big Bang, or after the end of inflation. And now I'm slightly stalling because I'm trying to go back to the beginning of my slide deck, because I just had to jump to the end. Okay, so back to the evolution of the universe. We've done Big Bang, we've done inflation, we've done particles, we've seen a bunch of questions that we don't have the answer to. Big Bang nucleosynthesis, what's going on with lithium? Then we reach the CMB, and at CMB, things get pretty clear. We know what's happening. But then we look forward and we see galaxies form. And now I can go back to the question that was asked before. Let me just bring up the phrasing before. Where was that question? Somewhere here. Why does non-baryonic matter give structure formation a head start? Great. So, early universe, you have a lot of particles bumping about, doing their stuff. Yeah, you'll never get bored of that fact. Me neither. I love that fact. It is amazing. So, in the early universe, you have particles bumping around, you have photons bumping into everything else, and at some point you have dark matter. And dark matter is just doing its own thing. It might be interacting somewhat with the other particles in the very early universe. It might be creating more dark matter. It might be having cannibalism. You can have cannibal dark matter where it eats itself. It's very cool. But at some point, dark matter breaks away from everything else. Now, at this point, the only thing dark matter can do is fall together. Dark matter is gravitational, and it feels a gravitational force. Everything else is busy bumping into each other, but dark matter can just kind of sit there and grow and grow and grow. It's kind of like the bear that's gone off to hibernate, right? Everything else is doing its own thing. Bear is just getting food, getting bigger, ignoring everything else, getting ready for winter. So you have dark matter, and it's going to start having this non-baryonic matter, this dark matter. It's going to start growing and growing and growing. Later on, this is going to cause a gravitational influence. If you have enough dark matter, you are bending space-time. And that means that when you produce the first hydrogen atoms, at the time when the photons broke away, the protons and electrons combined together, so you have these primordial hydrogen nuclei, you have the electrons coming together, photons break away, you produce the CMB. At this point, where are these hydrogen atoms going to fall? Well, they're going to follow gravity. So they're going to fall in the places where there's dark matter. So dark matter is sitting there, growing and growing. And now you have hydrogen coming together with it. So suddenly you have a region of the universe where you have a lot of density, and you're adding hydrogen and hydrogen and hydrogen. And at some point you put enough hydrogen together with the dark matter, and you're going to set off a star. And once you set off a couple of stars, you have a galaxy. So this non-baryonic matter is setting the scaffolding upon which all galaxies can form later in the universe. But now you might be asking, how did the dark matter know where to go? Why is it not uniformly distributed everywhere? And we can go back to before inflation, or at the time of inflation, when the universe was governed by quantum effects, by quantum field theory, by quantum effects in the early universe, where you had these fluctuations. We know that every quantum thing vibrates. You can have quantum vibrations. Every vibration is going to have an associated wave. You're going to have these waves in the early universe. Now, when inflation happens, these quantum fluctuations in the early universe are suddenly stretched during inflation. And what this means is that you're going to end up with regions in space-time where you have less density and more density. Like, space-time itself is not going to be perfectly smooth. It's going to be very, very, very slightly bumpy because of quantum fluctuations in the early universe. These very, very slight bumps are stretched by inflation, and then it leads to regions where you have valleys and mountains and space-time itself. So when dark matter is going to sit down and cluster, it's going to do it in the valleys because it's more energy efficient than climbing a mountain. So the same mechanism, this mechanism of quantum fluctuations in the early universe, makes space-time slightly bumpy. When the photons broke away during CMB, some of them had to climb these mountains, some didn't. This affects their energy, where we see hot photons and cold photons in the CMB today. And the same bumpiness in space-time set the seeds for the formation of galaxies. So, to answer your question, non-baryonic matter helps with structure formation by sitting there, not doing much else, and clustering and letting other things fall on top of it. But we can tell a story going through quantum fluctuations in the early universe stretched by inflation, producing the places where you have hot and cold photons, and at the same time setting the seeds for galaxy formation. And that is absolutely amazing, and I will never get bored of this story. Phew. So much info today. We do many questions, too many questions indeed. I am not doing a 6-hour show. Already 1 hour is exhausting. I gave a talk on Friday. I've had a busy couple of weeks. I was honestly about to cancel today's show, but I'm glad I'm here because this is fun. Okay, so history of the universe. Let's recap. We have a lot of funky stuff happening at a lot of different times. But we're now at the stage where we're forming galaxies, and we have dark matter doing its stuff, and we have dark energy doing its stuff. We have no idea what these are. We have no idea why they're doing what they're doing, why they did it at specific times, also big unanswered questions. So I want to recap, because I've just dumped 13.82 billion years of evolution of the universe on you with a lot of facts. I know it's been an information overload today, but my idea here is that I'm setting up a lot of stuff that we don't know the answer to, and a lot of things that I know that you might have follow-up questions too. Next stream will be a general Ask Me Anything again, and then you can come like last week you mentioned all of these things, can you elaborate? So I hope today I'm giving you ideas of stuff that you can follow up on and ask me a bunch of questions about in the future. So if you didn't understand everything today, don't worry. I just dumped 13.82 billion years of evolution on you. It's a lot, so don't worry if you didn't understand everything today. But I'm just going to very briefly show one of the slides that I had at the iTelescope talk I gave on Friday, which is open questions in the universe. So I think it should be almost up now. Yes, I just need to do one thing. And let me just hide that. Okay, perfect. So I'm not going to go full screen on this, but I am just going to very briefly show something here, which is open questions. This was one of the slides that I finished with. Don't we have galaxies that show no dark matter? We have found a couple of galaxies without dark matter. We are confused by them. We're trying to figure out why. Open questions that I mentioned during the iTelescope stream. What happened during inflation? This is this big one of inflation, question mark. What was inflation? What happened during inflation? How did it start? How did it end? What caused inflation? We have no idea. How were the first particles formed? And why did we form more matter than antimatter? We have no idea. These are open questions in the field. How many forces did we have in the early universe? Did we have 4? Did we have 3? Did we have 1? Did we have a theory of everything? Did we have a grand unified theory? How, why, what's up with dark matter, dark energy? When did they form? Why did they form? What are they doing? What did they do? What will they do? And what's up with lithium? And I can add to this slide, what's up with the Dark Ages, that big era of the universe that we know nothing about? So there is a lot of stuff in the universe that we don't know the answer to. I'm a cosmologist, I study the universe, it's a great topic, but there are so many things we don't have the answer to. And then you can get even more metaphysical and ask questions like, what is time? What was before inflation? What causes the laws of physics to act the way they do? Why do we live in a universe that just seems to support life? Why? And we can go down a lot of rabbit holes here. And this is what makes cosmology so fun. We have these big questions, and we don't know the answer to a lot of them. And I've realized my stream should actually have been called Questions in Cosmology, not Problems in Cosmology. I will actually change that. There are so many open questions. There are so many things we don't know the answer to. And another big question is like, do we have primordial gravitational waves? Are we ever going to find them? What are we going to learn from them? I've tried to do broad questions here, but you can also break it down into so many individual questions. Why is there a supermassive black hole at the center of every galaxy? Why do galaxies look the way they do? There are so many unknowns in the universe, and this is what makes science fun. The day I can answer all of these questions is the day that physics stops being interesting. So the point of today's stream was to dump a lot of information on you, but also to remind you that this is an active field. There is so much we don't know about the universe, and that is absolutely amazing. Often people here ask me questions. I'm like, I don't know, but the answer exists out there, so let me look it up, or let me ask somebody who does know. But these questions, nobody knows the answer to. It's not like I just haven't been keeping up with it. It's just like nobody knows the answer to these questions. Someday, maybe, we might figure it out. We might find primordial gravitational waves that will help us understand the early universe. We might understand the nature of dark matter and dark energy. We might find a clear signal of inflation. We might figure out why there was more matter than antimatter. We're pushing particle colliders to higher energies to tell us more about these things. But it also might be that we never get the answer to these questions, and that will keep the next generation of cosmologists busy as well. That is really, really cool. So I didn't even go in today to things like the Hubble tension, which is a problem we have in our standard model of cosmology today, or all the other problems that have cropped up with our standard model of cosmology today. This is just the overall big picture, the big questions we have. Very happy to follow the stream. Thank you. Thank you for joining. I'm really happy that you did follow the stream. And I hope that next to work you manage to relax and enjoy the rest of your evening. I do try to relax. I do have a pretty good work-life balance. I do relax in the evening, so thank you for that. But I do relax as well. I don't just do science all day, because nobody can just work constantly. We all need breaks and distractions and disconnections. I absolutely do relax in the evenings and disconnect. Possible that the metaphysical questions will answer the science questions. That is an interesting perspective, and that could open up to a whole new stream. The question of why the laws of physics look the way they do, you could answer it easily by saying, because they do. We just happen to be in a universe where gravity behaves like this. Is there a fundamental reason for it? Maybe not. Does there need to be? Maybe, maybe not. This idea that laws need to have a reason, or that the laws of physics need to have a purpose, is a very interesting one. One that I'm not going to get into too much today. There's plenty of good science outreach books about this topic out there. I'm not going to get into that. But yeah, physics is amazing. Science is amazing. And there's so much we know about cosmology. We can tell so many things. We can tell stories about the universe. We can use the cosmic microwave background radiation to explain 13.82 billion years of evolution. I just wanted to flash the CMB again. But there's so many things we don't yet know. And that is absolutely amazing. Maybe someday we'll get the answers. And if we ever do figure out the answers, I'll be here on Cup of Cosmology to tell you all about it. I have to finish with self-promotion these days. So thank you everyone for joining today. I know today I haven't really answered questions. I've just asked questions. Maybe someday we'll figure out the answers. But to everyone who asked questions, who asked clarifying comments, as always, thank you so much. Your questions are the reason I come here. If I just wanted to monologue, I would do a pre-recorded video. So I'm here for the interaction and for the questions. So I really appreciate people, whether it's your first time here or whether you've been following me for 7.5 years. I really do appreciate everyone coming in with the question, with the engagement. It means a lot to me. If you want to get in touch, contact at cupofcosmology.com. You can always email me. I don't answer promptly, but I always do try to answer. And I'm also on Twitter, DCHooper91. And I am also on Mastodon, which honestly I am using more than Twitter. And I'm not going to get into the rant I did once about Mastodon because I have completely changed my opinion there. I'm also on Mastodon, DCHooper91. I'm basically DCHooper91 on any social media. You can find me there. Do feel free to get in touch. As a person who wanted to go to Aachen for a master's thesis, please do get in touch as well. Happy to chat. Cup of Cosmology should be online next Sunday. Then maybe I'll take a break. I'm traveling in February. I've lost track of time by now. I'm traveling in February, so there will be a break in February. But Cup of Cosmology should be online next Sunday, same time as today. That's 7 p.m. if you're in Europe, 1 p.m. if you're on the east coast of the US, and 10 a.m. if you're on the west coast of the US. There is a time zone converter on cupofcosmology.com, so you can get the time zone converter there. Whew. Okay, now I'm out of breath. I'm tired. Time to head off. Thank you everyone for joining. It's been super, super fun. I hope to see you all again next week. And I hope in the meantime you all stay safe and take care of each other.